Hello. Thank you for joining us today for our presentation of a proposed autonomous space research vessel with the purpose of exploring the hydrocarbon seas of Saturn's moon, Titan. Our names are Orin Kierczynski, Charles Schertzing, Maggie Stagner, August Sturm, and Candace Wiwel, and we are NAME on Titan. We're a group of seniors from the University of Michigan's Department of Naval Architecture and Marine Engineering, and today we will present to you the findings of our senior design project. We will introduce you to a concept that provides a new design solution for exploring Titan's unique environment from the perspectives and specific expertise of naval architects. According to the Drake equation, it is unlikely that we are alone in the universe or even our own galaxy. One of the major factors that impacts the likelihood of life developing is the presence of liquid water. Titan is of particular interest because its methane cycle is similar to Earth's hydrological cycle. The interactions between the ground, the lakes, the clouds, and the atmosphere may give scientists information about how life on Earth formed. Titan also has a bedrock of ice and a mantle containing liquid water under the moon's surface. Beyond the search for life, we aim to collect data on what's in and under the lakes, as well as the marine conditions, such as waves and currents. Also, we'd like to know what the atmosphere is like above sea level. Our mission, to send a surface vessel to the hydrocarbon lakes, supports the scientific community's desire for further exploration and understanding of deep space and our solar system. This is of great interest for obvious reasons to the scientific community and to humankind as a whole. An important component of attaining this goal of scientific discovery and exploration is the distance involved. At its closest, there are roughly 1.2 billion kilometers between Earth and Saturn. This means that signals from Earth to Saturn, and therefore Titan, take a full hour and a half going either direction. This means that our vessel must be completely autonomous. We can't wait 3 hours every time we need it to do something. Orbiting around Saturn are 15 roughly moon-sized objects named after the Titans of Greek mythology. The largest of these bodies is our goal, Titan.
Given a spacesuit capable of handling the cryogenic conditions and an oxygen supply, a human could feasibly walk about Titan's surface. The 150 kilopascal pressure is not too dissimilar from Earth's 100 kilopascals, and the gravity is comparable to that experienced on Earth's moon. A walk about the surface would present some familiar geological features, like mountains, volcanoes, rivers, valleys, and lakes. Looking up, you'll see the thick, hazy atmosphere of Titan, a trait shared by no other moon in the solar system. We plan on landing in Kraken Mare. The hydrological cycle creates a larger methane concentration towards the polar regions due to precipitation flushing out the other elements. This produces a higher concentration of methane in Ligeia Mare, giving a density around 450 kilograms per meter cubed. Kraken Mare faces less of the methane flushing, resulting in an ethane-dominant fluid composition around 650 kilograms per meter cubed. This 650 kilograms per meter cubed is more comparable to the 1,000 kilograms per meter cubed water found on Earth, and also represents a far less volatile liquid than the methane-prominent polar seas. Deep space communication logistics play a role in where to land as well. To reduce cost, mission plans are to use direct-to-Earth communications instead of compiling a multi-layer mission paired with an orbital satellite. Direct-to-Earth communications produces an opportune window for signal, thus the mission is being designed for Titan's next summer period, 2047. The vessel will explore autonomously for a minimum duration of 1 year, collecting data while cruising at a rate around 0.2 meters per second. During the summer time period, the forecasted surface conditions are favorable for surface exploration. Wind speeds are not expected to rise above 1 meter per second, remaining around 0 to 0.3 meters per second for most of the mission. This presents a low wave environment due to ethane's wind speed wave threshold of about 0.8 meters per second. In general, the largest wave height expected in rare circumstances is 0.2 meters tall. We defined 5 stages of the mission: entry, descent, splashdown, information acquisition, and end of mission. As we're taking a naval architecture approach to a problem which has mostly been looked at by rocket scientists, We decided to leave items like the heat shield and rocket design to people who specialize in that area. Our main focus and scope thus became information acquisition, with a feasibility focus on splashdown and end of mission details. Upon splashdown and deployment from our heat shield, the vessel will operate autonomously via our acoustic depth sounders and camera navigation systems. The vessel is designed to be self-righting to prevent capsizing during deployment and in the event of unforeseen weather conditions. Although the detailed autonomy design falls out of our scope, we expect a fairly rudimentary system intended to prevent beaching while underway. Depth pings are relayed from the sensors to the computer, generating a bathymetry map while concurrently tracking its previous surface positions to build a map of the lake. If too shallow a depth is experienced, the vessel adjusts course until a more ideal depth is maintained. An important consideration for this project is feasibility. The difficulty of landing a rocket on a moon so far away from Earth is a serious obstacle, and as we aren't rocket scientists, we have to confirm that this mission concept is feasible. One of the ways we did this was by looking at previously proposed designs for similar missions. These are renderings of two previous proposals, a boat design as well as a submarine. Design work for each of these concepts was a collaborative between individuals at Johns Hopkins Applied Physics Lab, NASA Glenn Research Center, and Penn State Applied Research Lab. An early design decision was the choice between a submersible and a surface vessel. We chose a surface vessel because it allows for a more robust design with a simpler mission profile. The robust design is necessary because of the potential for so many unknowns regarding density, viscosity, and depth. With this simpler mission profile, we aim to solidify scientific knowledge to allow for future exploration on Titan. The major functions and capabilities of our vessel are detailed in the owner's requirements. Our vessel will land and operate on Kraken Mare, the largest lake on Titan. It will survive in all foreseeable weather and marine conditions. The wind on Titan is typically low, between 0 to 0.3 meters per second, and the temperature design point is to be negative 290 degrees Fahrenheit, around 90 Kelvin. At this temperature, the hydrocarbon lake is expected to be near its triple point, although freezing is not thought to be common, and the ice formed would sink instead of floating. All structures will withstand launch and landing forces equivalent to roughly 10 Gs on Earth. The vessel will be designed to be self-righting in case of capsize upon landing or any unforeseen weather conditions. The vessel will operate completely autonomously for a minimum duration of 1 year, collecting data while cruising at a rate around 0.2 meters per second. A 1-year mission profile was chosen because, given our design speed, this would allow for at least one north to south trip, achieving the scientific goal of characterizing the possible changes in liquid composition along the length of Kraken Mare. The vessel will be equipped with a power generation system capable of providing sufficient electrical power to the navigation, scientific package, and communication systems. The scientific package focuses on collecting information regarding the organic composition of the lakes, the lake bathymetry, and the marine and atmospheric conditions encountered. The vessel and heat shield are required to fit in the standard Atlas V aeroshell. These were the major limitations determined for an early stage design. However, this is not an exhaustive list. The vessel will comply with all international space law restrictions and U.S. regional jurisdiction. This is a rendering of our current design. We've named our design the Space Research Vessel Oceanus. In Greek mythology, Oceanus was the Titan god of the world's seas and waterways. We had to consider volume limitations in our design due to the Atlas V rocket payload fairing dimensions. The rocket system was arbitrarily chosen and not considered to be within the scope of the design. The vessel is to be nested in a heat shield within the payload fairing to prevent burnup upon atmospheric entry. Volume and mass limitations were observed during our design process to produce a concept feasible of being delivered with the Atlas V 500 series rocket. Our principal characteristics can be seen in the table to the right. We have an overall length of 4.04 meters, a beam of 1.56 meters, and a depth of 2.3 meters, making our vessel a bit smaller than an average-sized car. We aim to optimize the length, beam, and depth with respect to the rocket volume restrictions.
The upper hull required special material consideration to preserve material strength while allowing the antennas to transmit data, which requires a radio frequency transparent material. Silicon carbide was selected based on its known use in deep space telescopes, such as the one aboard the New Horizons spacecraft. This material is known for stability in cryogenic temperatures, and it has a similar fabrication process to aluminum. For the lower hull, 7mm thick aluminum was selected as the material. It has been proven as a justified material for space systems and exploration because it maintains toughness factors in cryogenic temperatures, avoiding a brittle glass transition. A 5 cm thick layer of Space Sea material insulation lines the inside of the entire hull. Due to the material properties of the upper hull, a significant portion of the vessel weight is placed at a high vertical center of gravity. To compensate for this weight and maintain a positive GMT, small permanent ballast weights totaling 70 kilograms were added to the bottom of the hull. The hull weight shown includes the upper hull, lower hull, and insulation. With the total weight of the vessel at 1,246 kilograms, the vessel is still well below the rocket payload restriction of 17,740 kilograms. The trim of less than 2 degrees will not affect the operation of the instrumentation. The general arrangements of Oceanus allow optimal use of all equipment and machinery. The arrangements are split into instrumentation packages based on function. We have a navigation package, a science mission package, a communications package, and the power generation machinery. The vessel is equipped with the necessary instrumentation to achieve autonomous navigation. This instrumentation package includes 2 acoustic sounders, 3 external cameras, a Doppler velocity log, an inclinometer, 2 inertial measurement units, 2 sonar side scanners, and a computer for data storage and processing. The redundant inertial measurement units also include accelerometers. Radar and LiDAR remote sensing are not operational underwater, so Oceanus operates with sonar sensing. The Science Mission Instrumentation Package includes all equipment which is required for the mission detailed in our owner's requirements. The LAMP meteorology sensor, miniature mass spectrometer, pressure sensor, temperature sensor, and turbidimeter allow the collection of data desired to study the methane cycle on Titan, the composition of the lakes, the marine conditions, and the atmosphere. To achieve direct-to-Earth communication, our vessel has a radio antenna and associated radio equipment, which will operate on the X-band. The radio antenna is arranged similar to a deck in order to obtain desired surface area to achieve quality communications to Earth. The combined estimated mass of the navigation, science, and communication instrumentation packages is roughly 124 kilograms. The maximum possible power draw if all instrumentation were to be run simultaneously is 660 watts. The Advanced Stirling radioisotope generator was selected for this design because of the reliability provided by thermal nuclear power. The ASRG uses heat from a decaying radioactive isotope in a general-purpose heat source to drive a Stirling generator to produce DC current. This design will feature 8 ASRGs, which will provide approximately 900 watts of power 13 years after commissioning. The ASRG is currently a developing technology expected to be completed in 2028. These generators were selected over the existing multi-mission radioisotope thermal generators because they are smaller, more efficient, and use 1/3 of the plutonium isotope. Each unit has a relatively small mass and volume at 32 kilograms and 0.136 cubic meters respectively. Due to their high operating temperatures and approximate 30% efficiency, the ASRGs also double as an internal heat source to keep the vessel's interior temperature suitable for electronics despite the cryogenic exterior environment. The 8 ASRGs, as shown in the rendering, have the largest quantity of mobile mass, so their placement is crucial to the hydrostatic properties of the vessel. They are located as centrally as possible within the vessel to maximize symmetry in weights and available volume. The arrangement of the equipment on board Oceanus allows for effective autonomous navigation, data collection, and communication to Earth. The placement of all other instrumentation and machinery below the radio antennas is required in order to keep sufficient antenna area for communications.
Given the hull geometry and weight distribution, we can now begin talking about vessel dynamics, beginning with stability. Due to low wind speeds, scientists do not expect waves to occur in Kraken Mare. However, little is known about the sea conditions, making seakeeping analysis infeasible. To still allow for operations in the unlikely case of large winds or high sea state, The vessel is designed to be self-righting. The bubble-like shape of the superstructure, along with considerations for longitudinal centers of gravity, allow Oceanus to return to an upright position for all heel angles. The stability curve generated by Orca 3D confirms this self-righting capability. Moving on to the vessel's propulsion system, a trade study was conducted to determine the best suited propulsion method for our design. Previous proposals expressed a desire for a trade of propulsion systems such as paddles, shafted propellers, pumps, water jets, thrusters, and podded propulsion. We also looked into other propulsion methods including aeronautic propellers, cyclorotors, magneto-hydrodynamic drives, mirage drives, and sails. We traded the methods based on 5 weighted categories: volume, efficiency, mass, arrangements, and reliability/robustness. A large emphasis was put on reliability and robustness, as our vessel will be operating with no access to repair or malfunction solutions. The trade study resulted in 2 methods emerging as a viable option for our design: shafted propellers and thrusters. A sensitivity analysis further proved a superiority for the shafted and thrusted type propulsions. In the end, the thruster system was implemented into the design. Many small vessels applications such as ROVs and AUVs operate with marine-grade thrusters, providing ample precedent for future design work. The ability for high maneuverability and industry-vetted technology makes the thruster system a competitive choice for the final design. To determine the needed thrust, resistance calculations were determined with special consideration to the non-traditional operating fluid. With a Reynolds number of 1.35 times 10 to the 5th, the vessel drag was determined to be friction-dominated. Hull resistance was calculated using the University of British Columbia, or UBC's, power prediction method for small ships. This method utilizes ITTC friction line to determine friction drag, while form drag is solved for using geometric characteristics of the ship with data from testing. The spreadsheet allowed for input values for fluid density and viscosity, so values were tailored for the Titan environment. The UBC method was also used for air drag. Fluid density was again changed to represent Titan's atmosphere. For the high wind case, the vessel's speed was kept constant at 0.2 meters per second, with a bow wind of 1.5 meters per second for a relative velocity of 1.7 meters per second. The appendage drag accounts for a considerable portion of the vessel's total drag due to several instruments being housed outside of the hull. Appendage drag was solved for each appendage assuming no flow interaction, and drag coefficients were determined by the approximate shape of each appendage. Using these methods, the total drag for normal operation was determined to be 2.89 newtons, and for the high wind condition to be 24.09 newtons. The vessel drag was used as an input to determine the required power for the propulsion system. The thrusters were sized to be 12.7 centimeters in diameter based on existing ROV thrusters and space available under the transom. The sizing and weight of the thrusters was found based on Earth models, but the required power and propeller efficiencies were found using actuator disk theory to better account for differences in performance due to changes in operating fluid. In addition to propeller efficiencies, power calculations included a Pevel gear efficiency of 98%. Powering requirements were evaluated for both normal and maximum wind operating conditions. The propulsion power used for the power mode consideration is the maximum wind value of 62.47 watts. Maneuvering of the vessel is achieved by the arrangements of the thrusters, where 4 thrusters are used for vectored-based thrust. 2 thrusters are placed on each side of centerline so that the vessel can still operate with only 2 thrusters so long as they are one on each side of centerline. A skeg was added to the design to ensure straight line stability. The skeg was based off of fishing boat skeg data due to similarities in length to beam and beam to draft ratios. The electrical analysis was done by determining certain sensor and equipment packages needed during a specific mode of operation. For simplicity, 2 modes of operations were analyzed: the surface cruise condition and the functional/communications condition. Operating with multiple modes eases the electrical strain on the system. The surface cruise condition is composed primarily of the navigation and scientific mission electronics, while the communication condition uses the antennas and radios to transmit stored data directly back to Earth. Future design iterations should result in more load conditions, as not all the scientific mission equipment will be running at the same time, making our load analysis a conservative estimate. The electrical 1 line was designed to meet a high level of redundancy and reliability. The system functions at 50 volts DC to accommodate the operating conditions of the majority of the equipment. Auctioneering diodes were used with multiple load connections to ensure that the load is being powered by one source at a time. If a fault in that system were to occur, another source would provide the power necessary to keep the equipment running. The number of sources per diode is dependent on the reliability of the system and mission requirements. For the purposes of this design iteration, 3 connections per package and thruster were implemented. 3 sources per loads is just an arbitrary configuration to explain our reliability-focused one-line design, but the number of sources could increase or decrease in future design iterations depending on specific instrumentation reliabilities. Each instrument or equipment package would be specifically made and custom designed for the given application, so more accurate reliability information won't be available until that equipment is produced. Another source of reliability and redundancy in the system is the physical design of the powering and propulsion. 4 thrusters are incorporated in the design, but if failure were to occur, the system would still be viable to run with as few as 2. The navigation system utilizes doubled equipment crucial to operations to prevent mission failure in the event of a single-point equipment malfunction. The VFDs and motors per thruster shaft are duplicated to provide another level of redundancy and reliability for the unit. As described, a large focus was put into making the system as redundant and reliable as possible. Given the nature and scope of the mission, operational success is an immense priority and there should be little margin for error.
Because of the stress we've put on operational success and reliability, it was paramount to design a structural configuration which could withstand anything that's thrown at it. The structure is made of 10 centimeter aluminum 5083 rolled bar with the instrumentation attached directly to the members. This alloy is also used in the Bradley fighting vehicle for a similar application. Generally, ship structural analysis includes longitudinal bending analysis. This is found by calculating the longitudinal strength, the loading conditions, and sectional areas. Because the waves on Kraken Mare don't exceed 20 centimeters, and because SRV Oceanus doesn't have dynamic loading, splashdown loads are several orders of magnitude larger than these typical ship loads. The highest loads which spacecraft are typically subjected to occur during takeoff and landing. This is especially true for Oceanus, which is expected to see accelerations of up to 98.1 meters per second squared, or 10 Earth Gs, during its splashdown into Kraken Mare. These are the loads which the structure was designed to withstand. Using these loading values, a finite element model was generated using Dassault Systems' Abacus FEA program. Although the loading of the structure would be dynamic, it was generalized into a quasi-static analysis for this project. The boundary condition utilized for this was an encastre condition, cementing the entire transom of the vessel in place. This is a worst-case approximation, as lateral movement would have reduced stress concentrations in this aft region. This analysis also utilized C3 D10 tetrahedral solid elements, and the loads were applied by taking the mass of the entire craft, except the structure itself, and multiplying this by 98.1 meters per second squared. This was then split up and applied at the mounting points between the structure and interior. Also, a gravitational load of 10 Gs was applied on the structure itself. The structure was then further analyzed by performing buckling analysis using Euler beam theory with the generalization of a pinned free beam. This figure shows the deflection magnitude inside of the model. The maximum, as you can see, is roughly 6.5 centimeters. The most important output from Abacus was the stress of the structure when all loads were applied. Staying within the ultimate yield strength of aluminum 5083, and if possible inside its elastic region, was an important factor impacting the design. This figure shows the stress distribution of the structure, with the largest stresses shown in the aft portion near where the vessel contacts the heat shell. An important part of any FEA study is the convergence analysis. For this study, convergence was found around 32,000 elements. The maximum von Mises stress is shown in blue, while the buckling stress is in yellow and the maximum yield stress of aluminum 5083 is shown in red. As you can see, there is a safety factor of 2.5 for buckling and a safety factor of just under 10 for the yield stress. This is in line with the structural design's overall intent to provide a lightweight but sturdy structure capable of withstanding any load that is likely to be experienced.
After we completed an FEA analysis of Oceanus' structure, we did an additional case study into the heat transfer between Oceanus' 8 ASRGs and Titan's atmosphere. The motivation of the study is to know if our instrumentations will be operating in extreme cryogenic temperatures or in their designed temperature regions of 250 to 300 Kelvin. Using STAR CCM Plus, a computational fluid dynamics software, we were able to successfully simulate the temperature contours of Oceanus' inner cavity, hull, and Titan's surrounding atmosphere. Oceanus is designed with 3 layers of insulation for the cryogenic environment. First is a neon-filled inner cavity, which is where the instrumentation lies, followed by a 5 centimeter thick Space Sea insulation that wraps the entirety of the inner hull, and finally an aluminum hull that is 7 millimeters thick, made from alloy 5083. The thickness of the 3 layers was modeled after the previous Titan submarine design. In this picture, you can see the geometric domain of the simulation, where the teal prism above represents the ethane-methane atmosphere, while the dark blue region below represents the ethane-methane lake. For this simulation, we kept Oceanus at a draft of 0.6 meters, but due to late-stage design changes, the final draft of Oceanus is actually 0.66 meters. The difference in draft is important to note, but due to the computational time, we are going to neglect the changes of the draft for this study. Additionally, where the fluid and gas regions meet is a free surface where free surface waves were created and temperature can flow between the 2 regions. Lastly, the light gray boxes to the right you see are mesh refinement volumes. Seen to the left is the final rendered mesh that consists of 4.6 million cells. In the 3-dimensional figure, you can see the shadow of the mesh refinement volumes as well as the fine surface wrapped mesh on Oceanus. A base size of 2 millimeters was used for all inner hull meshes, while a base size of 10 centimeters was used for both gas and fluid regions. The figure to the right is a profile view of the converged mesh. The 8 ASRGs are seen represented by a rectangular box in the inner hull and have a combined volumetric heat source of 3,488 watts per meter cubed. To accurately simulate the heat transfer between the ASRGs and Titan's atmosphere, 7 interfaces were created, each 10 millimeters thick with 6 prism layers per interface. The interfaces are illustrated as thicker black lines in the profile view. Additionally, the figure shows the free surface interface in the middle of the figure and the mesh refinement volume seen with finer mesh surrounding the hull. After the convergence of the mesh, a turbulent flow model was selected based off the calculated Reynolds number. A reasonable K epsilon turbulent model with a 2-layer wall treatment as well as a segregated flow was chosen. Lastly, a Beskies model was chosen to simulate Titan's gravity of 1.354 meters per second squared into the physics continuum to ensure the proper draft as well as free surface effects were recorded. After the correct physics and flow models were chosen for the simulation, an initial wind speed of 1.0 meters per second and fluid speed of 0.5 meters per second were chosen. These values were based on our design speed at the time of simulation and the expected wind velocity Oceanus will experience. The figures below are contour plots of temperature as the simulation is iterating to a steady state. Both the fluid and the wind have an initial temperature of 90 Kelvin, while the inner cavity has an initial temperature of 280 Kelvin. The 8 ASRGs will hopefully heat the interior of the hull to the design conditions of 250 to 300 Kelvin. As you can see, plenty of heat is being dissipated into the atmosphere, while it seems like none is being expelled into the fluid domain. However, the majority of the heat fluctuation is into the liquid ethane, but can't be seen due to the significantly high specific heat of liquid ethane. With a value of 2,200 joules per kilogram Kelvin, liquid ethane has a specific heat 500 times more than water on Earth. This means that heat is dissipated very quickly within the fluid domain, unlike the atmosphere, which only has a specific heat of 1.8 joules per kilogram Kelvin. Lastly, the profile view shows drastic turbulence created due to the rake transom as the temperature is being expelled. The turbulence indicates induced air drag that requires further research into. This video shows a 3-dimensional contour plot of the temperature on the inner insulation of Oceanus after 84 computational hours to steady state. The temperature seen in this plot is exactly what the instrumentation will directly experience if they are close to the Oceanus' hull. The plot indicates that the bottom of the insulation experiences a temperature range between 160 Kelvin to 230 Kelvin, will allow the instrumentation's operating conditions, while the region closer to the bubble experience a temperature range between 290 and 300 Kelvin. This plot brings up issues with our design and with cryogenic regions at the bow as well as along the keel. To fix this, more insulation will need to be added to the design in those regions, and a new heat study will have to be conducted. The results also show that the design of the antenna bubble does an excellent job of expelling heat into the atmosphere with its high surface area to volume ratio. This video is showing a three-dimensional isometric contour plot of the entire simulation region. The three-dimensional volumes seen are showing regions of coherent structures in space. The structures have very similar physical properties as well as velocities and are plotted with a temperature field function. The 3D rendering shows small boundary layers around the hull and the temperature dissipation into Titan's environment. The structures indicate that the flow around the hull is symmetric, and the majority of the heat dissipation happens quickly after leaving the hull. The turbulence seems to be centered around the design of the rake transom and should require further investigation. Additionally, the flow around the hull indicates the laminar flow regions where the four thrusters are located, confirming the placement of them has been idealized for the flow characteristics of the hull. A significant bow wake is illustrated by the blue cylinders wrapping around the hull and following the transom lines. This was expected due to our low Froude number and design speed. To prevent any environmental harm to Titan, following the end of mission transmission, the SRV Oceanus will complete her maiden voyage by beaching herself on the southern tip of Kraken Mare. The beaching of her 8 ASRGs will prevent unnecessary spread of radioactive material as the power source decays into its protective casing, with a half-life of 87.7 years. SRV Oceanus pushes the realm of the possible with its innovative and robust design. It brings a unique solution to the scientific community's planetary research with a naval architecture approach. SRV Oceanus has unmatched reliability and robustness for all of Titan's environmental conditions. With her 8 ASRGs and self-riding capabilities, Oceanus can handle anything that arises on Kraken Mare. With her key features ranging from autonomous navigation to direct Earth communication, SRV Oceanus is ready for its maiden voyage. So are you ready to take the next small step for mankind and join us in the future with SRV Oceanus? Thank you for your time. The five of us will be answering any questions regarding SRV Oceanus Friday, April 17th from 9:50 to 10:30.